Hi and welcome to this course on the basics of production. Our learning objectives are as follows. First, serialization, which explores the process of saving Python objects and models into files so that they can be used later. sklearn pipelines, which covers the process of streamlining our data pipelines. This allows us to perform data pre-processing and model training in a single step. And finally, refactorization. There we will learn how to integrate our code into a production environment by saving custom functions and their classes into their own files and reading them into our notebooks. When working with our models, we've had the luxury to be able to train the model before evaluation inside the same notebook. However, the more complicated models take a while to train and won't have the same predictions each time. This is partly due to some level of randomness. When it comes to production though, we won't be able to retrain the model on our dataset each time before making a prediction. Therefore, we need a way to save a model so that we can load it up and get a prediction whenever we need one. The best two libraries for this purpose are YAML for data structures and Pickle for Python objects. YAML is a library that allows us to save Python data structures as a YAML file. This is helpful if we want to store model parameters as a dictionary. In the illustrated example, we first import the YAML and OS libraries. We then define a basic dictionary for demonstrating purposes and create the directory for our YAML file. Next, we save the dictionary using yaml.dump and the file handling that's built into Python. Finally, we read the YAML file in a similar fashion using yaml.load. Instead of simple data structures, Pickle is capable of serializing and deserializing entire Python objects, even custom classes that we've written. One could say that Pickle is a more involved library for serialization. It can convert a Python object into a byte stream to store in a file or database, maintain program state across sessions, or transfer data over the network. In the illustrated example, we first create a custom class which uses a specs dictionary from the previous example to create an object. The representation method computes the official string representation of the object, which is a representation that has all information about the object. In this particular use case, the model name is returned. Again, we use Python's file handler to open a file before saving the object using pickle.dump. Similarly, after having opened the file with Python's file handler, we read the Pickle file with pickle.load. Once you've gotten your feet wet in basic sklearn modeling, you might find yourself doing the same few steps over and over again in the same project. To get to the next level, pipelines are your friend. Pipelines are a way to streamline a lot of the routine processes, encapsulating little pieces of logic into one function call, which makes it easier to actually do modeling instead just writing a bunch of code. Pipelines allow for experiments, plus when your modeling gets really complicated, it's sometimes hard to see if you have any data leakage hiding somewhere. Pipelines are set up with a fit, transform, predict functionality, so you can fit a whole pipeline to the training data and transform to the test data, without having to do it individually for each thing you do. Super convenient, right? In the illustrated example, we have a mix of numerical, categorical, as well as null values. In order to train a model, we need to, first, fill in the null values, second, scale our numerical data, third, one-hot encode our categorical data, and fourth, fit a model to the data. All of these steps will need to happen with the live data as well. In order to make sure that the aforementioned transformations always behave the same, we need to save all of the objects that perform those tasks. It would make things a lot easier if we could save everything as one object instead. Our end goal is a Python object that can fit onto our training data and then predict on our test and live data. This full object can be thought of as a pipeline. A pipeline can be described as a factory assembly line with machines at each step manipulating and transforming the data. A transformer is a name for a single step in the assembly line. In order for a transformer to be used in our pipeline, it must have the fit and transform methods. This should look familiar as our scalars had these methods. A pipeline is a Python object that wraps around a list of transformers. Therefore, in order to execute each of our transformations, we only need to call the pipeline. This may sound confusing, so let's show how this is done in an example. In this example, we have both categorical and numerical data. For the categorical data, we only need to use the one-hot encoder. We import the one-hot encoder class from sklearn and create the cat transformer object for later use. Next, we import the pipeline class, which is going to be our wrapper. For our numerical data, we need to handle missing values. Therefore, we import the simple imputer. We also need to scale our features. For this, we import the standard scaler. Feature scaling is a technique to standardize the independent features present in the data in a fixed range. It is performed during the data pre-processing to handle highly varying magnitudes or values or units. If feature scaling is not done, then a machine learning algorithm tends to weigh greater values higher and consider smaller values as the lower values, regardless of the unit of the values. Finally, since the numerical transformer performs two transformations, it needs to be its own pipeline. Next, we want the two transformers to perform on certain columns rather than the whole dataset. For this, we import the column transformer class and create the preprocessor object. Note, there is an extra argument for which columns each transformation should apply to. Finally, we import the linear regression classifier and thus can put everything together into a single pipeline with two steps: the pre-processing step and the linear regression step. Last, we fit our pipeline on the training data. You can see that the graphical representation of the pipeline clearly outlines the pre-processing step, which handles categorical and numerical data separately. It also shows us the actual linear regression step at the bottom. Once we have fit our pipeline, we call the pipe.predict method on the test data to get predictions. Now, all we need to do is save the model with pickle.dump. With data science, it's very common to have messy code. We are constantly creating new graphs and training various models. While organization is certainly helpful during the testing and exploration phase, it's mandatory in any production environment. Everyone needs to be able to understand at a glance how our model functions. More importantly, we need to be able to read code that has been factored. So what do we mean by refactored code? We generally accept the idea that we never want to write the same block of code twice. If we were going to use a number multiple times, it's best to save it as a variable. If we are going to perform the same action multiple times, it's best to write a function. While this is true for a single Jupyter notebook, it is especially true for a code repo of a data science team. An entire team will be performing similar data transformations depending on a specific project. A single data scientist will even have multiple projects with overlapping code. Therefore, learning to refactor code into the greater ecosystem is essential for any data scientist within a team. Abstraction, or the idea of exposing only essential information and hiding complexity away, is a fundamental programming principle, and there is no reason why we shouldn't be applying it to data science-specific code. Let's look at the following code snippets. The purpose of this code is to remove any rows that contain the value unknown in any column of the data frame and create a new data frame named complete.df that contains only complete cases. This can easily be rewritten using an abstract function, getCompleteCases, that's used in conjunction with the data frame. Note that we also changed the name of the resulting variable to conform to the PEP8 style guide while we are at it. The refactor step is a set of cyclic actions that can be repeated as many times as needed. The cycle starts with identifying a piece of code from the notebook that we want to extract. This code will be transformed to an external function, and we need to write a unit test that comprehensively defines or improves the function in question. Unit tests focus on individual units of source code. They are usually carried out by providing a simple input and observing the output of the code. Not every data scientist feels confident about code testing. This is especially true if they don't have a background in software engineering. Testing in data science, however, doesn't have to be at all complicated. It also brings tons of benefits by forcing us to be more mindful and results in code that is reliable, robust, and safe for reuse. Finally, let's see an example in action. In the lower part of the illustrated example, we can see that we are importing a function from a module. In particular, we import the MSE function from the util module. So how do we build the util module? Very simple. This is done by creating a directory named util and placing an init.py file with the contents depicted in the upper part of the illustrated example. Of course, the util module could contain more than one function. We can import from this file as if it was a library. Spoiler, this is a simplified version of what libraries actually look like.